No, they have one. I just have to go to IT and get it. But I always forget. So I haven't had too much of an issue. So hopefully this isn't an issue. So with the last part of 2.7, still working with derivatives. Yesterday we interpreted derivatives as a rate of or as a slope of a tangent line. So now if you are asked to find the slope of a tangent line, what you are first finding is the derivative, that is your limit, to get your slope. So geometrically or graphically, the derivative represents the slope of a tangent line at a point on a curve, or the slope of the curve at a specific point. So now, and this is just kind of building on ideas we've already talked about. We had talked about how we use that same limit to find any instantaneous rate of change. So therefore, for derivatives, the derivative f prime of a is the instantaneous rate of change of any function y equals f of x with respect to x when x is a. So this is just in general, knowing that a derivative is an instantaneous rate of change is a huge idea in calculus. Anytime you are asked to find an instantaneous rate of change, you are finding the derivative. And that'll be talked about throughout the rest of the year. So then the biggest application of derivatives in calculus is with velocity, position and then velocity. So the derivative f prime of a is the velocity of a particle with position function s equals f of t at time t equals a. We've talked about that idea using that same limit to find velocity. And then we also have a definition of the speed of a particle. So velocity not only gives you how fast, but it gives you or shows you the direction. It'll be positive or negative. Speed is the absolute value of velocity. Speed has to be positive. So the speed of a particle is the absolute value of velocity, so the absolute value of the derivative. Yes, it is physics. So in example 1, and I'm actually going to have you now that we went through problem 10 from the assignment, we have position. The position of a particle is given by this equation of motion. So s, or f of t, is the function 1 over 1 plus t. T is measured in seconds, and s is measured in meters. It says find the velocity, and then find the speed after 2 seconds. So I would like you, individually or in your groups, to find the velocity after 2 seconds and find the speed after 2 seconds. And remember, if it's helpful, you can leave a as a and then substitute in the actual value later if that is helpful.
Oh. Yeah. No, thank you. He just speak up. I need your map.
So when you're supposed to find velocity
Oh. What is speed? Variable. It's not a variable. So speed is just Oh. Oh. Negative. Oh. Wait, I'll come back, bro. How did you know that this was 1 plus 2 squared? How did you know that these cancel out to be 1? How do you know that this? How do you know that this is 1 plus 2 squared? Because you're what's 0? Yeah. And then 1 plus 8. I don't know. It came from somewhere. Well, you wrote down the wrong thing. That's your fault. Why did you continue it, Jared? I thought you were right. Well, now it makes sense. There you go, buddy. Good? Good, all right. Good. We get yeah, he got it. That's what I got. So, oh my God. Yeah, I like the concept of it.
All right, I think we all got it. Just double check. Well, yeah. That's what happens. I can't pause, so. All right. Just make sure you understand one comment I have is make sure you understand that the limit is your velocity. Velocity shows speed and direction, so then speed is the absolute value of the velocity. All right, example 2. And this is an idea, too, that we've already talked about. We talked more about it yesterday as well. It says let P of t be the population of the United States at time t. The table below gives approximate values of this function by providing mid-year population estimates from 1992 to 2000. I know, very up-to-date data. Interpret and estimate the value of P prime of 1996. So it wants, first of all, let's estimate this value. So if we wanted to find P prime of 1996, and all we know about the function P of t is what's given in this table, how do you find or estimate that derivative? Yes. So the slope, the best approximation we can get is the slope between the 2 points on either side of 1996 that are closest. Now, you haven't been given any problems like this. They do come up on the AP test, so you will have ones that practice this, but make sure you not only want to pick the points that are on either side of 1996 that are closest, but they also have to be the same distance away from 1996. So 1994 and 1998 are both a distance of 2 away. So just make sure they are equidistant from that point as well. So I would find the slope between these 2 points. So that would be $9,710,000 over 4, or divided by 4. So 2,427,500 is the approximate value or the best estimation we can get for the derivative at 1996. What would the units on the derivative be? People per year. It is a rate of change. It's not meters per second. All right, so this is the value. It then says to interpret. To interpret this, it's good to know what your units are. So in general, if it just asked us for P prime of 1996, you wouldn't have to give the units, but it's helpful when you know them to interpret. What's important for you to note is that a derivative or any rate of change is going to show an increase or a decrease. So to interpret this, you have to address the specific year it's talking about or at whatever value it gives you. So I could say in 1996, and this is showing, since it's positive, that the population is increasing by this amount per year at that time. So in 1996, I can say the population was increasing by 2,427,500 people per year. So kind of showing for the next year in 1997, you would expect the population that you had in 1996 to be that much higher, is what that is saying. And yes, now if we found that derivative for a different year, we would have a different rate of change. So it's definitely not linear. It's not that constant rate of change. You're just finding it in that instant to get the best approximation. Any questions on that? So some of the practice is going to be just interpreting what the values mean. So this next part, in example 3, this I want you to spend time in your groups discussing. We'll go through it. But you are given, so for all of this, you're dealing with this function f of t described at the beginning. F of t is the number of centimeters of rainfall that has fallen since midnight. T is the time in hours. It first asks you to describe the inverse function in words, and then think about what the domain and range of the inverse function would be. So what would your x values represent, your y values represent? And then in question 2, it's asking you to interpret these function values. So what would the function value f of 10 equals 3.1 mean? What does the 10 mean? What does the 3.1 mean? And then what does f inverse of 4.2 equals 16 mean? What does the 4.2 mean? What does the 16 mean? So take a look at these. I'll be walking around. We'll discuss, but I want you to think about these without me just telling you what the answers are.